Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled 555 Timer Astable Operation. Okay, so let's review what an astable multivibrator is. Another word for it is an oscillator, and it constantly oscillates between 0 and 1, 0 and 1, 0 and 1. And in addition to that basic functionality, we can define certain features about it, namely a period, a frequency, and a duty cycle. So what is the frequency? Well, it's the inverse, the number of cycles per second, inverse of the period. Okay, what's the period? Well, it's the time it takes for it to complete that period. Go from any recognizable spot on a repeatable waveform and go to the next time it gets there, you're gonna get the period. If you pick a different spot, a different recognizable spot, and go to another different recognizable spot, you're gonna get that same period. What's the duty cycle? The duty cycle is kind of a relationship between the time it's on with relation to the whole period. Duty cycle is typically expressed as a percentage where it's TW, the time it's on, divided by the big T, i.e. the period, times percentage. There's an alternate definition of period. If you could think about it, the whole period is defined into basically a time high and a time low. What is the whole period? Well, it's time high plus time low. Okay, and this is a super handy definition for what we're about to do, because you'll be seeing the time that it's high, there is going to be a certain path for a circuit, and then the time that it's low, there's going to be a different path for our circuit. And if you can calculate the time high and calculate the time low, you can easily come up with a whole period, and if you've got the whole period, you can easily come up with a frequency and additionally the duty cycle. This entire lecture is based off your understanding of the basic internal workings of the 555 timer. If you have never seen these things before, definitely go back, hit the monostable operation where I give a basic tour of the 555 timer. Let's just do a very, very basic introduction here. What was the 555 timer? Well, it's the 555. There's a voltage divider there. And what we set up in 5-volt operations, all it's doing is giving us reference points, and those reference points are being used as inputs to the comparator. So I've got a blue comparator there, the upper comparator, where there's a threshold on the positive input, and it's using the voltage divider for the negative input, the 3.3. Okay, I've got a second voltage comparator where its positive input is 1.6 volts, and it's comparing it to the trigger input on its negative input. What do those voltage comparators do? Well, those voltage comparators, if the plus is higher than the minus, it's true, 1. If the minus is higher than the plus, it's false, 0. What are those outputs of the comparators feeding? Well, it's feeding an SR latch. In this particular case, it's a modified SR latch. How did I modify it? I just flipped it upside down. Added 2 inverters so I can get a not Q signal there. But how does an SR latch work? Well, it works just like an SR latch. When I set it, I give a 1 on S, a 0 on R, it sets. Q goes to 1. When I reset it, I give R as 1 and S as 0. What happens? Q goes to 0. When I'm neither setting nor resetting it, what does Q do? It stays in the state that it was. Okay, finally we've got our transistor, and it's an NPN transistor. When the base gets a 1, it closes. When a base gets a 0, it opens. And what I'm talking about is that path from discharge to ground. So now we've done a review of the basic internal components of the 555 timer. Let's go ahead and use it in conjunction with some external devices to create an astable multivibrator. So what are we going to do? We're going to go ahead and tie the threshold input and the trigger input together. Okay, it's making a decision off the same point. Additionally, notice, however, the threshold is the positive input for its comparator. The trigger is the negative input for its comparator. Additionally, notice that the threshold is being compared to 3.3 volts, and the trigger is going to be compared to 1.6 volts. So we probably expect that we never simultaneously set or reset this thing, which is probably a good idea because you don't want to do that to an SR latch. We've got some external components, and just think of this here. It's a series connection. It's R1 in series with R2 in series with a capacitor. I do have a potential side path here through this discharge. What is that discharge going to? It's going to a transistor. And if you could think about this here, when that discharge transistor is hooked to ground, i.e. it's closed, what's happening? Basically, all current is going in that direction right there. And if there was voltage on that capacitor, it could potentially discharge through that same path. If that transistor was open, if there was no path to ground there, what would happen? It could potentially charge up. The capacitor would charge up. I know it looks like there's a path on that threshold and trigger, but it's a comparator input. It's just looking at that. It's not like it's a separate current path. One thing too is there is Previously in our monostable operation, i.e. one-shot mode, we had an external input. There is no external input for an astable multivibrator. Basically, you set this thing up, you power it up, it's going to constantly oscillate. Okay, it's going to constantly act as a clock signal. And before we go into all the mumbo jumbo, the technical details of how this thing works, I'm just going to give you a brief overview here. As the capacitor voltage is falling, what's happening here? The output is 0. As the capacitor voltage is rising, what happens? The output is a 1. Just think of it, when the capacitor is charging, it's not being discharged. Its current path is that way. If it's not being discharged, chances are that transistor is off. So that transistor state is off when the capacitor is charging. When the capacitor is discharging, what do you think the transistor is doing? It's probably on, and it's falling down in that direction. Very brief overview of how it works. Let's go ahead and see if we can put this in some initial conditions and go ahead and see how it operates. And honestly, you can pick any spot on this timing diagram and just say, okay, here's my initial conditions. And what you will do, you will see yourself return to that same initial condition. You'll repeat the cycle over again. As the name implies, you are oscillating. So let's go ahead and just pick ourselves an initial condition, and you'll see that we will return to that same initial conditions. The initial conditions I've chosen to begin our analysis of this, we're going to say that our initial state VC, the voltage across the capacitor, is between 1/3 and 2/3 of VCC. Let's just say it's 2 volts, and let's say it's increasing, so it's on the way up. If it's on the way up, what that means is Q is equal to 1. What are the inputs for the comparators? They're the same. What is it? It's 2 volts. Each one of those is going to have 2 volts on its inputs. What are the outputs for each one of those comparators? If this one is 2 and that one is 2, what is the threshold? Well, the blue one. So the blue one is comparing 2 volts on the positive with 3.3 on the negative. What's that going to be? It's going to be a 0. The trigger, the lower red one there, it's comparing a 2 with a 1.6. That is also a 0. So the outputs for both of those comparators are 0. What is that mode? Well, neither setting it nor resetting it. So we're going to stay in that particular configuration. What was our configuration? It's going to be a 1. Not Q. What does not Q do if Q is a 1? It's a 0. What happens for a 0 for an NPN transistor? It's open. There is no path. So what's happening here is we were between 1/3 and 2/3. The voltage is increasing. The output is 1. We're going to stay in that same spot. The voltage is going to continue to increase, and Q is still going to be a 1. And how does our current path look like? Again, the discharge transistor is off. There is no path to ground from there. So what's going to happen is all current is going to go into that capacitor, and it's going to slowly charge up. Okay, so what we're going to do is on our timing diagram is we were at 2 volts. We're going to continue to charge. Our transistor in this particular case is off, and Q is going to stay a 1. What happens when the voltage across the capacitor reaches to its VCC? Well, that's basically our next condition. Basically, capacitor is continuing to charge, hits 2/3 VCC. What happens there? Well, the inputs to our comparators change. So they're both at now 3.3 volts, 3.3 volts, 3.3, 3.3. What happens to this one? Well, that's a 0. The red one, the lower one. What happens to this one up here? It's basically 1. It's no longer in that condition. And let's just say, just for sake of analysis, it goes slightly higher than that. Because there is a little bit of hysteresis there. Slightly higher than that, it goes to a 1. We're having a 0, 1. What are we doing here? We're resetting that flip-flop, that SR latch. What happens? Q goes to a 0. Okay. What happened is not Q. Not Q goes to a 1, and that transistor turns on at that moment. So again, what did we do? Q went down to a 0. The transistor turns on. At that moment, what is that current path? Well, this one right here is now suddenly hooked to ground. Whatever voltage was on that capacitor, it discharges through R2 only. Now, this is a critical point right here. Look at the difference between this diagram. It's discharging through R2 only. Whereas when it was charging through R1 and R2. Think about it. When it's charging, our tau is R times C. What's R? It's R1 plus R2. C, for that is the charge. What is the discharge tau? Tau discharge is still R times C. What's R? R2C. Okay, one would stand to conjecture R2 is a lot smaller than R1 plus R2, because that makes sense. The discharge time will probably be smaller because it's only discharging through a single resistor. There are tricks you can do to potentially get a different relationship like that, which we'll discuss a little bit later. But go back to what I said earlier. When it's charging up, it's a 1, the time high. When it's discharging, it's a 0. That's the time low. This right here, this relationship that we just discovered here is very crucial to time high and time low. This is going to be related to time high. This is going to be related to time low. There is some difference, however, because realize that we are going from 1.6 volts to 3.3 volts. We are not going from 0 volts to 5 volts. So it's a partial charge all the way to a partial discharge to a partial charge. So there is a modification to this, and we will show you some of the math involved with that. Basically, time low is 0.7 R2C. That's something I would remember. We'll go into this a little bit later. Time high is 0.7 R1 plus R2C. I would probably remember that. So we have different taus, different behaviors for the charge because it's going through 2 resistors versus the discharge where it's going through 1 resistor. But I digress. I've already given you the answer there. Those time highs and time lows are very critical to the operation of this thing. Let's continue though to make sure that we get back to that same state. So what's happening when it discharges? Well, it's discharging through a single resistor, and as we said, according to our timing diagram, the time that it takes to discharge is probably going to be a lot faster than a time that it took to charge. There's going to be a certain point, however, when it discharges to 1.6 volts, basically the input for the second comparator here. So let's go ahead and look at that. So VCC falls below 2/3 VCC, but hasn't hit 1/3 yet. So what I'm saying is discharging now, it's between 3.3, but hasn't hit 1.6 yet. So what's happening here? Okay, so obviously Q is a 0, not Q is a 1, and it's going to continue to discharge on our current path through here. And what's going to happen to those inputs? Let's say we're back at 2 volts again. Okay, so our inputs for each one of those is 2 volts, but we're on the way down now. So it's discharging, it's slowly decreasing, but we're currently at 2 volts. What are the outputs for each one of those comparators? This one's going to be 0, and because the input is on the trigger, the positive input is constant at 1.6, 0. So we're currently going to be in a 0, 0 output, 0, 0. Our mode is going to be stay. It's basically going to stay in that configuration where Q was 0. So it's going to continue to discharge until it hits 1/3 VCC. What happens then? 1/3 VCC happens. Basically, we are getting 1.6 volts there and 1.6 volts there. What's the output for the top comparator? It's going to stay as 0. What's the output for the bottom comparator? That's no longer in a true condition, no longer in a an imbalance condition, so it's going to go to 1. So what's happening here is we are setting it. We are not resetting it. Obviously, the mode is set. What does Q do? It goes to 1, not Q goes to 0. And what does that transistor do? It turns off. Once that turns off, there is no discharge path. And what does it start to do? It starts to charge again. So Q has jumped up to 1 because it's been set. Not Q goes to 0. It turns off the transistor, and we're going to start to charge up. We're currently at 1.6 volts. What do? We continually charge up, and guess where we're back at? We're right back at our initial conditions which we started to, and it's going to charge up to 2 volts. Okay, so we've got our 2 volts on our threshold and trigger inputs. What are the outputs for each one of those comparators? It's going to be 0. This one's going to be 0. When both zeros and 0 is on set and reset, what mode are we in? We're in the stay. Okay, so we're going to stay at Q is equal to 1, not Q is equal to 0. Basically, it is going to be in that charging condition. Like I said, we're currently right back to where we started, and we can repeat this sequence over and over and over again. So now that we've developed basically our punchline formulas for the time high and the time low, respectively, time high is equal to 0.7 R1 plus R2 times C, because again, it's charging up through both resistor 1 and 2, and then time low is discharging through only R2. It's 0.7 R2C, and again, graphically, what's that look like? As it's discharging, Q is 0. As it's charging, Q is 1. So if I can go ahead and figure out what this time high is and that time low is, what I can do is add time high plus time low to get my total period T. If I want the frequency, it's 1 over T. If I want the duty cycle, it's time high divided by T, typically expressed as a percentage. Question remains is where does that 0.7 come from? Well, it comes from our basic formulas for charging capacitor. I'm not expecting you to do this right here, but I'm just giving you guys the origin of that mysterious 0.7. It's because we are not allowing this thing to charge all the way up to 5 volts, nor are we allowing to discharge all the way to 0 volts. That's what that 0.7 is coming through. Recall, we've got two separate formulas here. Our first one for a charge, our general formula here is the voltage across the capacitor is equal to final voltage plus parentheses initial voltage minus final voltage parentheses e to the negative t divided by tau. What is tau in the charge case? Well, it's R1 plus R2 times C. What are we solving for in the charge case? We're solving for that time, t. What is t when it's charging? Well, it's the time high. Okay, as that voltage is increasing, Q is 1. Okay, so what we're going to try to do is solve for that. So what we do is we put in our initial conditions. Our final voltage, if we left this thing alone, would be 5 volts. What was our initial voltage though? It was charging up from 1.6 volts. If we left it alone, it would charge up to 5 volts. What we're trying to solve for is T, knowing that we are going to stop it at 3.3 volts. How long does it take to get there? The answer is T. Solve for T. How do you do that? Take that, subtract 5 from both sides, you're going to get this. Divide by negative 3.3, you're going to get this. 1/2 equals e to the negative t divided by tau. Take the natural log of both sides. What you get is negative 0.7 equals negative t divided by tau. Get rid of the negative. Move tau over to that side. And again, what is tau for our circuit? Forgot the c right there. Okay, so it's R1 plus R2 times c times 0.7. That's why that mysterious 0.7 comes in. Discharge. Exact same thing. We're going to use the general formula for our discharge. What's the general formula for our discharge? Slightly different than the charge. It's the initial voltage times e to the negative t divided by tau. What's tau in this particular case? Well, it's R2C. What's the t that we're solving for? It's time low, because as it's discharging, t is equal to t low. So go ahead, put it in our initial conditions. It was at 3.3 volts. We did not allow it to charge all the way to 5 volts. So at 3.3 volts, the voltage is going to decay from there. What's it going to decay to? It's going to decay to 1.7. At what time? T. That's what we're solving for. Go ahead and divide by 3.3 on both sides. Get 1/2 is equal to e to the negative t divided by tau. Take the natural log both sides. What you get is negative 0.7 equals negative t divided by tau. Get rid of the negative both sides. Solve for little t. And again, what is little t in this particular case for the discharge? It's time low. What is tau for this particular case? It's only discharging through R2. It's R2C. So our final answer is 0.7 R2C. Where does that 0.7 come from? Mathemagic. But just go back to this diagram right here. The time high is 0.7 R1 plus R2C. The time low is 0.7 R2C. And just think of those diagrams here, just back to our initial two diagrams. So our initial two diagrams show a single current path. It has to charge up through R1 and R2, and because there is we're going from 1/3 to 2/3, we've got to put that 0.7 in. Now let's look at this here. Our discharge path is only going through a single resistor, but because we're charging from 2/3 down to 1/3, what are we getting there? It's 0.7 R2C. So let's go ahead and give you guys some values here and figure out if you can figure out the period, the frequency, and the duty cycle. Okay, let's go ahead and do some example problems here of a 555 timer configured for a stable operation. For our first example 1 here, we've got resistor 1 is equal to 1 kilo ohm, resistor 2 is equal to 1 kilo ohm, and the capacitor is a 0.047 microfarad capacitor. And physically, to hook these things up, again, you take your 8-pin 555 timer, and you're going to go ahead and take R1 and R2 and C1, configure them in a series path where R1 has a discharge between R1 and R2, and our threshold and trigger inputs are being tied together. It's sensing the voltage at the capacitor, so we can go ahead and make those decisions. So what you go ahead and do is you go ahead and calculate. What we're going to try to do is find for the whole period. We're going to try to find for the frequency. We're going to find for the duty cycle for each one of these. And how you do this is, again, is just use those formulas that I've given you. Time high and time low. How do those relate? Well, the whole period is equal to time high plus time low. What's the frequency? It's 1 over t. What's the duty cycle? It's time high divided by the whole period. Okay, now think again from the perspective of the current paths. When this is charging, it's going through two resistors. They're two identical resistors. When it's discharging, what's happening? It's going through a single resistor. Okay, and if you could think about that, it's one time constant for the discharge, two time constants for the charge. And if you've done everything correctly with two identical resistors, you should probably get a duty cycle which is 2/3. It's charging up 2/3 of the time, discharging 1/3 of the time. If you go ahead and run the numbers here, what you're going to get, a time high for this particular configuration. Let's go ahead and draw a diagram. So your time high is going to be 65.8 microseconds. Your time low, 32.9 microseconds. Time high plus time low is going to be 98.7 microseconds. Your frequency, roughly 10.1 kilohertz. And like I said previously, should be roughly a 2/3 duty cycle. What's happening there is 65.8 divided by 98.7, you're getting a 66.6% duty cycle, 2/3 duty cycle. So it makes sense. All right, notice here the duty cycle, it's greater than 50%. Can I get something less than 50%? Let's say I'm going to make that discharge time as long as I possibly can. As long as I possibly can. I'm going to crank the value of resistor 2 way up. So the discharge time, i.e. this time, is going to be super long. Okay, can you get something less than 50%? The answer is no, you can't, because check this out. You're still charging through R1 and R2, so your charge time will still be larger. I know you're discharging through R2 and it's really big, but you still have got to add both these guys together. In this particular configuration, let me go ahead and wipe out the diagram. So in this particular configuration, i.e. for example 2 now, we're going to go ahead and have a large resistor on resistor 2, a small resistor on resistor 1, we're keeping the capacitor the same. So time high for the second configuration is going to be 164.5 microseconds. Time low is going to be 131.6 microseconds. Okay, yes, you have increased the time it took to discharge, but still realize the time it took to charge was longer than a time to discharge because it's going through both resistors. You go ahead and add up time high plus time low to get our full period T. What do we get? We should be getting 296.1 microseconds. 1 over T. What am I getting there? 3.38 kilohertz. What's my duty cycle? Well, time high, 164.5 divided by my whole period, 296. I'm getting a duty cycle of 55.5%. Still not less than 50%. So when you hook it up in a traditional configuration like this, you're going to have problems getting duty cycles less than 50% if you require something like that. Okay, so there is kind of a cunning trick to this, and the point is basically look how it's charging. It has to charge through two resistors. What we want to do is we want to create a situation for situations less than a duty cycle of 50%. We only want it to charge up through one resistor, and how you do that is just offer a side path to it. And you guys have seen a device in semiconductor devices and circuits, namely a diode. Okay, what I can do is I can put a diode in this configuration and watch what happens here when it's charging now. What is my time constant? What's going through that diode? My time constant for the charge configuration now is R1C1. Basically got rid of this guy. What is the discharge path? Well, the diode is reversed biased. It's still R2 and only R2. Again, this is a totally ideal magic diode that has no bias voltage across there. And be aware that we'll have some current going through R2 in that particular configuration. Let's say it was plus to minus 0.7 volts. Realize there is plus to minus 0.7 volts across R2, so a little bit of current will go through because again, elements hooked in parallel have the same voltage across. But let's just say it's a magic diode. Reach into box, you pull out your magic diode, there is no voltage drop across it. What are you going to get for a particular configuration like this? Well, your time high, because it's only going through R1. Again, we're using this configuration here. It's only going through R1. Your time high will be 32.9 microseconds. What's the time low? Well, it's still the exact same one we had before because we're going through a 4K only. You're getting 131.6 microseconds. What's your whole period? Well, it's TH plus TL, getting 164.5 microseconds. And your frequency in this particular case is 6.1 kilohertz. What's your final duty cycle with that magic diode in there? 20%. So you got something substantially less than 50%. But be aware, look what happened to that frequency. That frequency is not the same. Okay, let's say you needed something that was 20% at 3.38 kilohertz. You can't just take that diode. There's a bit of interplay between these components. And like I drew in an earlier diagram in the monostable operation, there are graphs which show capacitance on the vertical axis and the frequency on the other axis. I'm going to draw a real quick one right here. And this is the graph I'm referring to here. We got your capacitance on the vertical axis, your frequency on the horizontal axis. And what does that R represent? It represents this combination of R1 plus 2R2. So there's some internal manipulations to that right there. So let's say that's a 1K and here's a 10K, and your chosen combination of resistors where it's R1 plus 2 times R2 is going to be 10K, and you want this frequency right there. What do? You walk up to that 10K combination, walk over to that capacitance and pull that capacitance or the closest one of common component values out of the box. You should hopefully get that frequency. Additionally, I know I've shown you these formulas for time high and time low. You can get all values from those formulas: period, frequency, and duty cycle. And these are the formulas that I choose to use because I can get all values. They are shortcut formulas. If I know resistor 1 and resistor 2 and capacitor, what I can do is go directly to the frequency. Frequency is 1.44 divided by R1 plus 2R2. See, that's why those graphs are drawn that way, referring to this graph right here. If you've got a known combination of R1 and 2R2, you can go ahead and solve for your capacitance for a given frequency. Again, I don't necessarily use that formula because I like using these formulas right here because they give me everything one might need to know for a quiz or a lab that you're about to do. Okay, this concludes the 555 timer astable operation.